Hello, everyone. In this lecture, we want to talk about a very famous theorem in calculus known as squeeze theorem. This squeeze theorem is also known as sandwich theorem, and I'm going to say why is it like that. So imagine we have three functions here. We have g of x, h of x, and f of x. And let's assume that h of x is in between f of x and g of x. Okay, so the top function is g of x. It's some sort of polynomial function maybe. And then we have this f of x, which is the lower function. And then in the middle, there is another graph here, graph of function h of x, which is sort of squeezed in between the two graphs of g of x and f of x. So it's like sandwich in between. All right. And also, we know that the limit of f of x when x approaches c, okay, c is the point that we are interested in. Limit of f of x when x approaches c happens to be equal to limit of g of x when x approaches c, and both of them are equal to L. Okay, so that is the assumption here. A limit of g of x, limit of x when x approaches 0 is equal to L. Both of them are equal, and also our function h of x is squeezed in between these two functions. If this happens, if this scenario is true, then we can conclude, or this condition implies that limit of h of x when x approaches c is also, I repeat, also equal to the same number L. Now, what was L? L was limit of g of x or limit of f of x. So now we're saying that the graph or the function that is squeezed in between these two functions will also have the same limit value of L. That's what we're saying here. That's what squeeze theorem states. So an example here, it says limit of x times cosine of ln of x equals what when x approaches 0 from right hand side. Ln of x is the natural logarithm of x. Cosine function, everybody knows about it. And x approaches 0 from right hand side for an obvious reason, because the logarithmic function is not defined for negative values or even 0. Therefore, x has to approach from right hand side so that this natural logarithmic function be defined to begin with in first place. Now, to do this question, to find this limit, we are going to argue the following. We're going to say whatever ln of x is, whatever angle it represents, end of the day, cosine of that angle has to be between 1 and -1. So this is inevitable. So cosine of ln of x is always between 1 and -1. Nobody can say no, because that's the cosine function. That's the range of cosine function. In fact, that's also the range of the sine function. Sine and cosine functions always fluctuate between 1 and -1, obviously. It is a fact. Now, if you multiply all three sides by x, you get -x less than or equal to x times cosine of ln of x less than or equal to x, okay? And it's needless to say that limit of x when x approaches 0 from right side is equal to 0. And it's also needless to say that limit of -x when x approaches 0 from right side is also equal to 0. So limit of the function on the right side is 0, limit of the function on the left side is 0. And now we want to find the limit of the function that is squeezed or sandwiched in between these two functions. So what we're going to say, according to the squeeze theorem, we can say that limit of x times cosine of ln of x when x approaches 0 from right side is also equal to 0. And this conclusion, I would say, as per the squeeze theorem, okay, we can say what we just said. So you see, it's a very handy, very nice tool to use in calculus. It will be hard to find this limit, initially, but when you notice that it's a function that is squeezed in between two other functions whose limits are actually both equal to 0, therefore you say, according to squeeze theorem, that limit should also be equal to 0. There's another example here, limit of x squared times sine of 1 over x. When x approaches 0, we want to find this limit. So again, we're going to say sine of any angle, even 1 over x angle, is a value between 1 and -1, and nobody can argue with this. And if you multiply all three sides with a positive value of x squared, we get x squared times sine of 1 over x less than or equal to x squared. And then we can argue that limit of x squared when x approaches 0 is the same as limit of negative x squared when x approaches 0. And both of them are actually equal to 0. And our so-called function x squared sine of 1 over x is squeezed in between these two quadratic functions, x squared and negative x squared. Therefore, according to the squeeze theorem, one more time, we can say that limit of x squared times sine of 1 over x when x approaches 0 is also equal to 0. Okay? This theorem might not be in your textbook, but we just learned about it in university. It is used a lot, and it doesn't harm to know more, to learn more, and it doesn't harm to be able to find limits of like complicated functions like this function, which is like partially trigonometric, partially logarithmic, partially linear. And I hope you understood the application of squeeze theorem in this short mini lecture. Thank you for your attention.